Good day. The topic of my presentation is PMU missing data recovery using tensor decomposition. Synchrophasor measurements are being used more in power systems. However, PMU can have missing data caused by communication network congestions, divide error, sensor failure, or cyber attack. PMU data has naturally three dimensions: time, location, and type of variable. Time and location are consistent. However, for the type of variable, voltage and frequency are bus measurements and current are branch measurements. And in order to solve this issue, we propose to use bus-oriented structure, where for each bus, a current injection is calculating using Kirchhoff's law, and all data is organized into bus-oriented tensor, which is multidimensional array. Tensor has a time dimension, location dimension, and the variable dimension. And variables are voltage magnitude, voltage angle, current injection magnitude, current injection angle, and frequency. Bus-oriented tensor is used in the following algorithm to recover missing data. So we first decompose the data, and then we use tensor reconstruction to recover missing data. Here we have the description of polyadic tensor decomposition. We start a disordered tensor A, which has n1, nk up to nd are the sizes for each of the d dimensions, and polyadic decomposition is defined as the sum of rank 1 tensors up to rank r, and each of the rank 1 tensor is the outer product of factor vectors up to order d. Here there is example of polyadic decomposition of third order tensor. So we have the summation of rank 1 tensors up to the rank r. Reconstruction of the tensor from the decomposed form can create error that we would like to minimize. And we define the difference between two tensors, original and reconstructed, as delta A, and we're trying to minimize it in this optimization problem when we are minimizing the Frobenius norm of this difference. Here we have an example of missing data recovery using a simple three-dimensional tensor B. We delete the first row of the first slice in this tensor and decompose it using polyadic tensor decomposition. Because the rank of the original tensor is 2, we have just 2 rank 1 tensor to represent it. And then when we reconstruct the tensor from the decomposed form, we have the first row of the first slice recovered. At the bottom, you can see an example of the calculation. So we have the corresponding values from the factor vectors of the first rank 1 tensor multiplied plus the corresponding values of the second rank 1 tensor multiplied. And we can get the correct answer for the first element of the first row of the first slice. We tested the proposed approach on real PMU data from New York system. The data came from 19 PMUs, 100 inverted current channels, 52 voltage channels, and 19 frequency channels. We deleted 16 seconds of data from one PMU that had 3 current, 2 voltage, and 1 frequency channels, and recovered it from the proposed approach. As you can see, recovery trajectory closely follows the original trajectory before data deletion. At the bottom, you can see the root mean square error of the recovery. Frequency has the lowest error because frequency is the global trend. Voltage magnitude has a little bit larger error because there is still trend, but it's more on the original level in the power system. And current magnitude has even larger error because for the current magnitude, the similar trend can be observed only on this one substation or a group nearby substations. Still, the error is relatively small, and it justifies use of this method in real-world applications. Thank you for your attention.